This last unit that we're going to learn about is solutions in acid-base. And a solution, if you remember back to the beginning of the year, is a homogeneous mixture that does not settle out. Now, homogeneous meaning it's the same consistency throughout. A solution is made up of two pieces. The solute, that's the part that gets dissolved, and the solvent, the part that does the dissolving. So again, just to summarize that, the solute is what gets dissolved. It is what is dissolved. The solvent is what does the dissolving. Most of the time, the state of matter of what's left when you mix two things together is the solvent. Water is called the universal solvent because of its ability to dissolve many, many substances. Now, the process of solvation is the process by which we create solutions. Another way to think about this is surrounding each solvent with, solute particle, surrounding the solute particles with solvent particles. The solvent is going to always outnumber the solute in almost every single solution that we will make. Now, a special type of solvation occurs when we have water as our solvent, and that's called hydration. Here we have two examples of hydration. Actually, the same example taking place would be sodium chloride, NaCl, being made into aqueous NaCl. When we put in that crystal, it will split into sodium +1 and chloride -1. Water molecules, that's what each of these Mickey Mouse looking characters is, will move in to surround the sodium. Notice the negative oxygen end faces in toward the positive sodium end. This is due to the polar charge, or the polar affinity of the water. Now notice the opposite is also true when we look at our chlorine over here. The positive hydrogen end, hydrogen here and hydrogen here, faces toward the negatively charged chlorine. This right here, this process is called solvation. More specifically, this is called hydration because we are surrounding with water. So when we're dealing with solutions, it's important to think about why they occur. And for the most part, the reason that they occur is the same for both ionic and covalent compounds. And that reason is because the attraction in solution is greater than staying the way it was, or staying undissolved if you want to think about it like that. So when we're talking about, and this actually applies to both, when we're talking about ionic substances, you're really looking at, well, is the solute more attracted to the solvent or itself? In the case of sodium chloride, both the chlorine and the sodium are more attracted to water than they are to each other. Now, it's not a like type thing, it's a based on energy, and it's less energy required to be with water than it is to be with each other. Not all substances will dissolve all other substances. The rule that we like to follow and use is like dissolves like. Now what this means is that a polar substance such as water will dissolve anything that has a separation of charges, like anything that's ionic, for example, or anything that's polar covalent. On the other hand, something like, say, turpentine or nail polish remover will only dissolve things that are nonpolar based, for example, pine tar. There are several reasons that actually will cause the reaction rate to differ. And those causes really stem from the fact that they change the number of collisions of the molecules. So here we have three pictures, and I don't know if you could really figure out what's going on, but the first picture here is an example of shaking. Shaking, or stirring, or in some cases scratching, are all different ways that we can agitate a mixture. And agitating a mixture causes it to increase in terms of its rate of dissolving. So think about if you want to make a nice pitcher of lemonade. You would put in your powder mix, you might put in your sugar, and you could let it sit there, and over time it would work around with the water molecule movement and it would become dissolved. However, if you want to drink that lemonade right away, you might grab a wooden spoon and stir the whole thing up. Another thing we can do, this picture over here on the right, is that we can actually increase the surface area. By increasing the surface area, you're actually increasing the number of collisions. Though most people actually make their Kool-Aid or their lemonade in a pitcher, the most effective tool in your kitchen for actually making that lemonade or that Kool-Aid would be like a cookie sheet. The cookie sheet, which is very, very, shallow, but very, very wide, has a great surface area. And the greater the surface area, the more the number of collisions that will occur. The final picture that we have is this one down here. And that is a picture of a thermometer in the sun. And that is really meant to show you that by increasing our temperature, we can also increase our number of collisions. So really three ways that we can affect the rate of solvation or increase that rate of solvation. We can shake it, stir it, scratch it, called agitating. We can increase the surface area, or we can increase the temperature. All of these things will lead to an increase in the number of molecular collisions. The more molecular collisions, the more solvation that occurs.